When I had the idea about making these videos, it was this topic I'm going to talk about today that I was most looking forward to. Basically, what we're going to do is look at something in set theory, which seems like it's totally fundamental, okay? This idea of taking the product of two sets. I mean, this is such a basic thing. It's like in science, if we didn't know how to multiply numbers together, science would be completely ruined. And in a similar way, this notion of being able to take the product of two sets is really, really basic. And it seems like it's a really, really fundamental thing, but it's not. So what we're going to do today is to sort of peek behind this curtain of category theory and see how this idea of products are really defined in terms of category theory. And we're going to be rewarded for this. My gosh, we're going to be rewarded. So there's three different special things that we get out of this. One is that we're going to get a new notion of product, the so-called categorical product of two objects. And this is a notion which can be applied to all sorts of different mathematical objects. We're going to be able to think about the product of monoids. We're even going to be able to think about the product of two categories. And then the second great thing is that the way we're going to approach this is just such a generalizable method. I mean, we're going to look at this idea in a very basic kind of setting, this idea of sets, and we're going to think, how can we generalize what's going on into terms of category theory? And simply thinking about that approach is so beneficial, because loads of these glorious concepts from category theory come from just taking that approach, from just thinking, well, there's something I'm interested in, and how can I write that in terms of category theory? But the third thing we're going to get out of this is, in my opinion, definitely the best, and that's simply the definition of this categorical product itself, because the definition is just so deep. I mean, it's based around the notion, really, of perfection. So the way that we're going to define this categorical product is essentially as a sort of perfect object with respect to a particular property. So this idea of things being perfect has really been a more of a philosophical idea than a mathematical one for most of history. But in these days, with category theory, we can really start to see how to formalize that kind of notion. And I think this is very great. I mean, I actually think that there's going to be quite a few really important implications of this idea of taking the product of things in category theory terms and the sort of underlying ideas. I believe that they're going to have a lot more impact and lead to a lot of new developments that we haven't even seen yet. Now, to explain a little bit about what it is, this is the context that we're going to think about products initially. So if you have a set which has elements A and B, and we have another set which has elements 1, 2, and 3, then there is something called the Cartesian product of those two sets. And this is something that's normally just defined in terms of set theory. So we'd say it's the set of pairs, with the first entry in the pair belonging to the first set, and the second entry in the pair belonging to the second set. And this is a very nice idea, because if we have a line, we could represent that by the real numbers. Okay, so on this number line we have 0, 1, 2, -1, and so on. And we also have these numbers between. And the real numbers are a sort of model of all of the numbers on this number line. And then if we take the Cartesian product of this line with itself, then we basically get the plane, okay? Because as Descartes realised, you can refer to any point on the plane with a couple of numbers, x and y. X being the amount you have to move right of the origin, and y the amount you have to move up from the origin. So we can think of the plane as the Cartesian product of the line with itself. This is also written as r squared. Similarly, r cubed would be the Cartesian product of the plane with a line, which gives you all of three-dimensional space. And it's a very interesting idea because we can then think about things like r to the power of 4, and that would represent four-dimensional space. Okay, so we're going to focus on this idea of the Cartesian product of two sets, and we're going to look at this idea, and I want you to pay close attention to how we actually arrive at this definition, because that's really it's really a very important aspect of it, because the way that we arrive at this definition of a categorical product is basically to see what's going on in sets and then think, well, how do we express that in terms of category theory? And so whenever you see some process that you're interested in, you can think, well, how do I express that in terms of category theory? And if you're able to do so, you get a kind of categorical definition of that thing, and then you can apply it to innumerable other cases and find interesting things. So it turns out, for example, that this definition of a categorical product that we're going to cook up, we can apply it to other categories as well. So here I have another category where the objects are positive integers, positive whole numbers, and we'll draw an arrow from one object to another if the first number divides the second number. So 2 divides 6 because 6 is equal to 3 times 2. So we draw an arrow from 2 to 6. And then we can ask, for example, what happens if we apply this definition that I'm going to explain, and we say, well, what's the categorical product of this object here and this object here? And it turns out that this is going to be the greatest common divisor of these two numbers, the biggest number which divides into both of them, which is 2. So this hopefully gives you a flavour about how this definition that we're going to arrive at can be applied in lots of different places. Okay, so here comes this definition of the categorical product, and the way we're going to get there is to look at what's happening in this category set, and we're going to think about how we get the Cartesian product of this set A and this set B. So this is just the set of all pairs with the first entry from A and the second entry from B. And what we're going to do is we're going to ask ourselves, how can we pick out this object by referring to things in terms of category theory? So in category theory, this set here is just an object. Just think of it like a dot. And this is another object. And this is another object. So how can we identify this object in terms of the arrows in this category set? Now these arrows in the category set are functions. So let's think about the functions involved with these things and see if we can pick out the nature of this thing in terms of functions. So what kind of functions do we know about this? Well, we know that there is a sort of special function which goes from this set here, this product, to the set A. And that's the one that just takes the first entry in a pair. So we can call this function pi1, and it's basically sort of like a projection. We're sort of projecting down onto the first entry in the pair. So we can draw that in our category theory picture here. So there's A times B, and there's A, and there's B. Now similarly, we're going to have a projection from this set here into B that just takes the second entry in the pair. And that's pi2. So there it is, pi2. So we're getting towards this definition of a categorical product. We know it's something that has we know it's some object that has an arrow into A and an arrow into B. Now that's obviously not enough to uniquely identify this thing, but it's a start. And so we're going to use that to define something. We're going to call it a product candidate, okay? So it's something that might be a product. So this is our definition of what we mean when we say something is a candidate for being a product of A and B. And we just mean that it has some arrow F into A and some arrow G into B. In my case here, I'm calling the arrow F pi1 and the arrow G pi2, okay? So clearly this is a product candidate, and it's represented in category theory terms here. But that's not enough, obviously, to pick out this as actually being the Cartesian product of this set here and this set here. The Cartesian product being the collection of all these pairs. So what else do we know? Well, here is the very interesting idea. What we do, we say, well, what if there is another candidate? So let's pick out another candidate. So there's another candidate X, and it does have a function into A. Let's make one up. And it does have a function into B. So there's another candidate. Now, what we're going to do, so I'll just draw that in terms of category theory. There's our other candidate. Now, there's one more important thing that we know, and that is that whatever this candidate can do, I mean, what I'm saying it's doing these functions here into A and B. And the idea is that whatever it can do, this sort of perfect object can do better. What do I mean by that? Well, what I mean is that, say we want to apply this function f from x to a. Well, there's a way that we can instead do a function into this object here and then apply pi1 to obtain the same thing. And similarly, there's a way to sort of simulate what's happening with this function g. And there's a unique way to do that. and that's the definition of the product. So what does this unique way look like? Well, it's going to be a function h and the way it's going to be defined is it's going to send an element of x to the element f of x, g of x. That way, this thing here is going to get sent to f of x, g of x. When we project its first component, we're going to get the same result as doing f. And similarly with g. So let's draw that. So p here gets sent to 1 under f, and it gets sent to a under g. So let's send p here to 1, a. And q here gets sent to 1 under f and b under g. So let's send 1, so let's send q to 1, b. And that does the job, okay? So all we're going to do now is to formalize this in terms of category theory, and we're going to have our definition of a categorical product. So all we have to say is that from this candidate with its functions into a and b, there's going to be this unique arrow h that makes this diagram commute. What I mean by it makes it commute is just that when we have two paths from one object to another, then those two paths give the same result when we compose all the arrows within them. So this is our definition then of a categorical product. We're saying that it's an object that has an arrow into A and an arrow into B, and for any other such object, for any other sort of candidate with its arrows F and G, there's going to be a unique arrow H which has the property that it makes this diagram commute. Okay, so this is the proper definition then of the categorical product. We're saying that it's a candidate, so that just means it's an object which has an arrow into A and an arrow into B, and it has the property that whatever any other candidate can do, it can do better in some sense. So what I'm exactly saying is that if we have any other candidate X, any other thing which has an arrow into A and an arrow into B, there's a way that we can simulate the effects of this arrow F and this arrow G. And there's a unique way of doing it. This is very important, okay? So we're saying that there exists a unique arrow and a unique sort of intermediary arrow, H, with the property that pi1 after H is F and pi2 after H is G. So can we see that this is indeed the categorical product of this object here and this object here? Well, yes, it has an arrow into A, and yes, it has an arrow into B, so it is a product candidate. And also for any other product candidate, we can make an arrow from that candidate into our product object here, an arrow like this, which sends an element x into f of x comma g of x. And we also need that this is the only function which sort of makes this diagram commute. And is it? Well, I think it's you can see that it is, okay, because we'd have to send an element x to f of x comma g of x. If we didn't, say we sent the first entry to something different, well then when we do pi1 and just grab that first entry, it wouldn't match up with the way f maps it. And similarly, if we didn't send if we didn't send x to something with a second entry which was g of x, then when we did pi2 on that pair, we wouldn't end up with g of x, but we have to in order for these conditions here to be satisfied. So hopefully you can see now that this is a categorical product. Hopefully you can see that the Cartesian product of two sets is the categorical product of those two objects, of the two sets, of the two objects representing those sets in this category set. But you may still be wondering, well, okay, so I can see that the Cartesian product of two sets satisfies this definition, but how do I know that this definition is correct? I mean, maybe there are some other things which satisfy this condition which look nothing like the product of two sets, okay? So I have to then try and argue the converse. I have to try and argue that something that satisfies this condition in the category set is actually the Cartesian product, okay? And so how to do that? Well, the way that that works is very, very interesting, and it's a lot easier than you might expect, because it turns out that in general, in a general category, any two objects which satisfy this condition, any two things that we could call A times B under this condition, are actually going to be isomorphic to each other, okay? So this basically says that, if you have some category and you're saying, okay, what's the categorical product of these two objects? And you think, well, it's something that satisfies this condition. Well, there may be many such objects which satisfy this condition. So which one do you pick? Well, they're all isomorphic, so in some sense it doesn't matter. And we're going to demonstrate that later, and I'm also going to recap the definition of what an isomorphism is, so you can recall that. So let me just reiterate this definition of a categorical product. So in a general category, if we have a pair of objects, then a categorical product is going to be an object which has an arrow into each of them, and it has the property that for any other object with an arrow into each of them, there's going to be a unique arrow which makes this diagram commute, in the sense that these paths, like along here and here, this composition gives the same as this, and this composition here, pi2 after h, like this, gives the same as g, okay? So there may be many arrows from this candidate here, x, into our actual product, but we're just requiring that there's exactly one which makes this diagram commute in this sense. Okay, so this is the definition of a categorical product, and there may be many categorical products of an object, and there may not be any. Okay, we're not guaranteed in an arbitrary category to be able to find something like this, but in many nice categories we're lucky enough to be able to find these things, and when we can, we have a natural sort of notion of what products are of objects from that category. And if there are many such objects which satisfy this condition, they're all going to be isomorphic to each other, and I'm going to demonstrate that to you later. Okay, so a particularly easy situation to understand what the categorical product is in preordered sets. So a preordered set is just a category which doesn't have any parallel arrows. So there's at most one arrow from one object to another. And in situations like that, we don't have to worry so much about arrow composition, because whenever we have two arrows head to tail, we know their composition has to be in the category, and there's at most one arrow which is the composition of this one and this one. So we don't actually have to go to the effort of labeling which arrows are the compositions of which other ones, because there's only one possibility. And that makes the definition of a categorical product much simpler, because those parts of the definition which involve thinking about what the actual composition of arrows is and checking that the composition of these two is indeed that one and so on, we don't need to worry about that. The definition of a categorical product for a preordered set is much more sort of visual, geometric, if you like. And basically, for a preordered set, we have an object which I'll preemptively call A times B is the product of A and B when for any x with an arrow from x to A and an arrow from x to B, we have that there's an arrow from x to A times B, the product. Okay, so that's what this definition of a categorical product looks like in a preordered set. Not in general, but in a preordered set. In a preorder. And that's a category where we don't have any parallel arrows. Okay. So what does this look like? Well, here is a couple of objects A and B in this preordered set. I haven't drawn the identity arrows, but you know, imagine they're there as well. So we want to work out what's the categorical product of these two. Now, there won't always be a categorical product, even in a preordered set. I mean, there may not be any objects which have arrows to both of these things, for example. But in this case there are. And so what are the possible candidate products? Well, they're going to be objects which have arrows into both A and B. So there's going to be three of them. This one here, this one here, and this one here. But this one here has the property that there's also an arrow to it from any other candidate. And because this is a pre-order, there's only one arrow into it from any of these other candidates because there's no parallel arrows. But anyway, this gives us a rather nice sort of visual way to think about what a product is, at least in this context. So if you think about rivers, you can think about sort of watersheds. Okay, so imagine this river is flowing and then it sort of forks into two. And if you have one object up here, let's say A, and one object here, let's say B, then both of these objects are going to be accessible by any object over here, but the product is going to sit right at the sort of watershed of these two rivers, because you can reach A and B from it, but anywhere else, sort of further this way along the stream, also has the property that you can reach A and B from it, but you can also always reach A and B, this product from anywhere further along this stream. Okay then, so I wanted to remind you about the definition of an isomorphism in category theory. So recall that we started thinking about isomorphisms and what they meant in this category of sets, where the objects represented sets and the arrows represented functions. And in that context, an isomorphism is a function which has a sort of inverse. It's one of these one-to-one onto mappings, which just pairs things up in a sort of one-to-one correspondence. So basically the definition so in terms of category theory, an isomorphism is going to be an arrow from one object to another, such that there's an arrow in the opposite direction, and if we compose these two arrows starting from A, we go to B and then we go back again, then their composition gives us the identity arrow of A. And similarly, if we start at B and we compose this arrow into A and then the arrow back again, then we get the identity arrow of B. So this is the definition of when F is an isomorphism. When there exists G such that G after F is IDA and F after G is IDB. Okay, so speaking of cats, I can identify that our cat has been walking around in this room because there are footprints of chalk all around, and I think it's been stepping around in this chalk dust here. But anyway, let's get back to talking about isomorphisms. So I want to show you that if we have two objects and they are both categorical products of A and B, then these two objects have to be isomorphic. So what we're going to do, we're going to start by thinking about things from the perspective of this product here, A times B. Now, it sees this other thing here as a candidate product. There it is with its arrow into A and its arrow into B. And so we have the property that there's a unique arrow, a unique intermediary arrow H into A times B, with the property that if we go along H and then pi 1, we get pi 1 bar, the arrow from this thing. And similarly, we can get this arrow from going along here and then here, okay? So now let's flip around and think about things from the perspective of this. This is also a categorical product. And so there's going to be an arrow the other way, which we can call H bar. And this has the property, sort of the opposite way round, that If we think about this as a candidate, there it is with its arrow into A, well, we can simulate that by going along H bar and then pi 1 bar. And similarly, pi 2 is equal to pi 2 bar after H bar. Okay? So let's write down what we know, considering this. So we know now that pi 1 bar is equal to pi 1 after H. So we know that because this is a product. And we also know that pi 1 is equal to pi 1 bar after H bar. And we know that because this is a product. Okay, so now we're going to consider, we're just going to sidestep a little bit, and we're going to think about a sort of degenerate case of this candidate comparison type of job we have to do when we're defining a product. So we're going to say, okay, this is our object, and can it do what itself can do? Okay, so there is our product with its projections into A and B, and then we want to compare it with itself. So this, we'll now think of this as a candidate, and there it is with its projections, pi 1 and pi 2 into A and B, and we're wanting to know, can we replicate the effect of these projections with some intermediary arrow? And indeed we can. If we just pick the identity arrow, then yes, we have the property that going along this arrow and then projecting gives the same as this arrow, and going along this arrow and projecting this way gives the same as this arrow. So indeed, the our product does work out when we compare it with itself. Now what we're going to do is to notice that if we go along H bar and then we go along H, we're going to get an arrow which goes from A times B to A times B. So we're going to draw that as a diagram that looks a bit like this. So now we've redrawn the diagram. We've sort of tried to illustrate what's going on, some of the stuff that's going on here. Okay, so we've drawn another diagram where we have two copies of A times B. But now I've just, for no reason which is apparent yet, I've just drawn this arrow, H after H bar, which goes from A times B to A times B. Now I want to convince you that this is a intermediary arrow from this object to this object. So what I'm saying is that if we think of this as our product, and we think of this as a product candidate, then this arrow has the property that if we compose it with pi 1, we get pi 1. And if we compose it with pi 2, we get pi 2. And we can see this from the algebra. Okay? So if we just substitute this equation here into here, we get that pi 1 is equal to pi 1 after H bar. And by similar logic, pi 2 is equal to pi 2 after H bar. And that's what we wanted. We wanted that pi 1 is equal to pi 1 after h bar, and similarly with pi 2. So that means that this is an intermediary arrow that makes this diagram commute. But here's the clever part. Remember the definition of a product. We said there's only supposed to be one such intermediary arrow which makes the diagram commute. And here we have one. So if we only have one and we see two expressions for it, those expressions must be equal. So we have that h after h bar must equal id of a times b. And that's just the exact, well, by similar logic, sort of just flipping things around and looking things from the perspective of a bar, a times b bar, we can get that h bar after h is equal to the identity of a times b bar. And this exactly means that h and h bar are isomorphisms between these two products. So there we have it. The reason why two categorical products of the same objects have to be isomorphic to each other. I think it's remarkable that it's possible to do all this stuff just by thinking about arrows. So just as a bit of a tangent, I noticed that there's a sort of vague relationship between this idea of a categorical product and a very interesting idea by the physicist Alexander Wisner-Gross, who had this very interesting notion that you could define intelligence. I'm putting it very roughly, but he said that you can define intelligence as something that tries to maximize the number of possible actions that it can do. And if you think about the categorical product in those kind of terms, you could almost say that it's the most intelligent of the product candidates, because it can do whatever any of these other product candidates can do. And it does so with great economy by just using these intermediate arrows. So now we have this fantastic tool, this notion of a categorical product. We can just point it at a category and ask, is the categorical product defined in this category? And when it is, we usually have some kind of natural notion of what the products of objects within that category might mean. So, for example, we can consider this category of monoids. So remember, a monoid, we can think of it as a category which just has one object. So I told you in the last video about this idea of what we might consider to be arrows between these objects in this category, what we might consider to be an arrow between monoids. And so we have this category of monoids, we know what the objects are, they are all the monoids, and we know what the arrows are. They basically correspond to functors from one monoid to another. And now we can ask, is there a natural notion of the product of a pair of these objects in this category of monoids? So can we think of how it's natural to define the product of one monoid with another? And when we go through the work of it, we find that there is a very natural definition. I'm going to tell you it a bit later, but just to illustrate how it works, we have this monoid where, so this is the categorical view of a monoid as an object with these arrows. The sort of normal view is that it's some set with some operation. And we can then ask, so it's some set with some operation which takes a pair of elements and outputs another element which is associative and which has an identity element. So these elements here in this set will just correspond to the arrows in our monoid. So here's an example, the kind of standard example, which is just the whole numbers with addition as our operation that gets us a new element from the old ones. And we can ask, what's the product of this monoid with itself? And the result is a very natural one, because we can think of this monoid as the number line and an element as a point on this number line. It's an integer space. Maybe I'll use this one. And then we can take a couple of elements and just literally add them together to get the new one. And the product, it basically consists of the plane. So an element in this new monoid we get from producting these ones together will be a pair with the first element from the first monoid and the second element from the second monoid. And we can just add these pairs together. So for example, 1, 2 plus 1, 3, can you guess? It's going to be 2, 5. Okay, so we get this very natural notion of taking the product of two monoids, which is exactly how people defined it before they knew about category theory. And it just comes from the categorical products notion. And I'm going to tell you exactly how this product of monoids works in a bit. I'm going to define something first, and then we'll have a very succinct definition of how we can take the product of two monoids. Okay then, so now we have this tool of the categorical product. We can point it at any category that we like and then see, can we define the categorical product within that category? We've already pointed it at the set and found that the categorical product yields this notion of the Cartesian product, which is a very natural way to take the product of sets. So now let's take the bull by the horns and see what happens when we point this categorical product tool at the biggest and most important category that we know about so far, which is this category of all categories. Okay, so what does that mean? Basically what that means is we're wondering if there's a natural notion of taking the product of a pair of categories. Is there a way we can get a pair of categories and somehow make a new category that can be considered to be their product? And that's what I'm going to tell you about, because it turns out that there is a very natural definition. Now, we're not going to worry about how this relates to the notion of categorical product, which I've been discussing so far. I'm simply going to tell you the result. I'm just going to tell you what this natural notion of taking the product of two categories is. Okay, so let's say we have a category C and a category D. Well, I've drawn the product of these two categories according to this definition that I'm going to explain over here. Okay, so what is it? Well, it has objects which are pairs. The first element in the pair is an object from C, and the second element of the pair is an object from D. And all such pairs are appearing here as objects. So if you like, you could say that the set of objects of this product thing are the Cartesian product, is the Cartesian product of the set of objects of C with the set of objects of D. So we're writing the definition here. The product, C times D, of a category C and a category D, it has these objects A comma A bar for each A, which is an object of C, and each A bar, which is an object of D. And we also have arrows in this product category, and we get those in a very natural way by taking arrows from over here and arrows from over here. So in this product category, we're going to have arrows F comma F bar, which is going to be a arrow from A comma A bar to B comma B bar. And we're going to do that for every arrow F of C and every arrow F bar of D. Okay, so whenever we have an arrow F from A to B in C, and we have an arrow F bar from A bar to B bar in D, then that's going to give us this kind of paired thing, F comma F bar in this product, and that's going to go from A comma A bar to B comma B bar. Now, the only other thing you need to know is how are we going to compose these arrows? And it's very straightforward, actually. It's remarkably straightforward. So let's say we have an arrow G comma G bar and an arrow F comma F bar in this product. And we want to compose those together. So we want to find out what is G comma G bar after F comma F bar. Well, all we do is we look at what's going on over here, and in this category C, we compose G after F, and in this category D, we compose G bar after F bar, and then we just pair them together. So G comma G bar after F comma F bar is G after F, comma G bar after F bar. Okay, so all we're basically doing is composing these arrows in a natural way. Okay, so I've explained to you now what the objects are of this product and what the arrows are and how to compose them. You may want to satisfy yourself that this is indeed a category. Think about, for example, does this thing have identity arrows? Indeed, the identity arrows over here are just going to be the product. So, for example, ID A, ID A bar is going to be the identity arrow of the object A bar. Okay, so it will have identity arrows, and it's also associative because the arrow composition is just basically working just like it worked in C and D, just with this comma here. Okay, so it is indeed a category. It has identity arrows and it's associative. If you're feeling adventurous, you might want to try and convince yourself that this actually is what you get if you ask what is the categorical product of a pair of objects in this category of categories. So now we know how to define the product of two categories. It's very easy then for us to return to this category of monoids, remember, which has objects as monoids and these arrows as transformations from one monoid to another. And we can ask, well, what's the product of a couple of monoids? How do we define that? And it is exactly the notion of the product of categories which we've just been explaining. We simply think of these monoids as single object categories, and we apply that definition we've just been discussing, and we think, oh, this is a category of one object and this is a category of one object. If we take the product of these two categories, we get another one with one object, and it has these arrows which are sort of pairs of an arrow from here and an arrow from here, and the way that they're composed is as I discussed before. So we're really because these definitions are so nicely related, we don't have to do too much work to get a notion of what a natural idea of products are for this category of monoids.